Good morning, dear listeners. My name is Andrii Bielinskyi, and today I would like to present you our paper, which is titled as Lyapunov exponents as the indicators of the stock market crashes. And actually, I would like to thank the organizers for the opportunity to present our study.
At first, we are going to talk about the motivation of using such indicators, present the concept that is related to Lyapunov exponents. Then, I will give you a short definition of what is chaos and how it differs from randomness. Then, I am going to say about data, which is used for our calculations. And definitely we cannot go without theoretical background of our algorithms. And then, as usual, I am going to make some conclusions. The anticipation, prediction, and identification of financial critical states is a huge challenge. Thus, we refer to the theory of complex systems, namely to the apparatus of chaos theory, and we obtained a method from recurrence quantification analysis that behaves in a similar way as our indicators from chaos theory to give reliable indicators of such critical states. So chaos, in common sense, is associated with something unpredictable, and it's not completely true. We could say that chaos can be presented as deterministic. Sometimes we can see clear patterns in such systems that are proclaimed to be chaotic. So I would say that the same initial conditions usually lead to the same final states. But because of initial sensitivity, that is the main characteristic of chaotic systems, final states can be different. So if you change your initial parameters with some little value, the final results become unpredictable in long term. Random behavior is non-deterministic. Even if you knew everything that can be known about a system at a given time in perfect detail, you would still not be able to predict the state at a future time. However, even random systems are not completely unpredictable, because we can express them statistically through the probability distributions or give some confidence interval for our predictions. And again, for small errors in chaotic systems, the probability distributions of final states can differ, but in most cases it's simply due to our inability to measure the initial state of a system accurately enough and follow it accurately. Speaking again about initial sensitivity, here we can see two trajectories that start initially close to each other, and as you can see with some time t, they diverge, and this divergence happens exponentially fast, with some characteristic exponent alpha. And about this characteristic exponent I'm gonna talk from the next slide. So that term lambda is interesting for us Lyapunov exponent. It quantifies how fast converge or diverge trajectories that start close to each other, quantifying the strength of chaos in the system. In such cases, when our system is multidimensional, we have as many Lyapunov exponents as the dimensions in it. The existence of at least one positive Lyapunov exponent is generally seen as a strong indicator of chaos. Positive LE means that our system diverges exponentially fast, indicating about chaos. Close to zero Lyapunov exponent means that trajectories neither diverge nor converge. Negative LE means that our system converges, so it becomes more stable. And exactly the largest Lyapunov exponent is used to quantify the predictability of the systems. Also, the largest Lyapunov exponent starts to dominate with some time, and it starts to bring much more information comparing to other exponents. Throughout our research, we found that there are very little papers that are devoted to the construction of Lyapunov exponents as predictive indicators in the stock market. Therefore, relying on methods and tools described in our previous papers, we emphasized three the most well-known and correlated stock indices, specifically DAX, Hang Seng, and SP 500. And we constructed for them indicators that should indicate in a specific way to the crash events. Main crashes were emphasized, relying on the list of stock market crashes and bear markets. And further research were made for DAX index because of the limitations of this paper. All calculations were made for normalized returns, or it actually can be done for log returns. And we used a sliding window approach with the size of 500 days and 1000 days. With the great interest in Lyapunov exponents, more and more methods and proposals for their calculation have appeared. Unfortunately, there hasn't been obtained acceptable and universal method for their calculations. Thus, we consider it one of the most popular. For the largest Lyapunov exponent, we consider it a method proposed by Rosenstein. For the spectrum of Lyapunov exponents, we consider it Sano and Savadas method and Ekman and Toll method. And also we consider it one of the measures from recurrence quantification analysis that is similar to Lyapunov exponents. At first, I would like to start with the description of Rosenstein's method. So at the beginning, we construct embedded vectors according to Duncan's theorem. Then we need to find the corresponding neighbors of each point on the trajectory, which temporal separation is greater than the mean period of the reconstructed time interval. Therefore, we consider each pair of neighbors as nearby initial conditions for different trajectories. More concrete, it is assumed that the each considered pair of nearest neighbors diverge approximately at a rate given by the largest Lyapunov exponent. So here we have a set of approximately parallel lines with a slope roughly proportional to the largest exponent. So the largest exponent is then calculated as the slope of the average line, defined via a least square fit to the average line. So this process is the key for calculating accurate value of largest Lyapunov exponent. So according to Ekman's algorithm, similarly to previous example, we construct a banded vector with a dimension d sub e. Then we are trying to find neighbors of each trajectory in our orbit that lies within suitable radius r. Then, as described in third step, we would like to obtain the matrix dimension d sub I that projects our trajectories on the next step during the evolution. But here we would like to determine this matrix not with dimension d sub e, but with d sub m, that would define this projection locally and yield spurious Lyapunov exponents, because we actually could reconstruct our system with probably larger dimension that it needed. Thus, our local dimension d sub m should be less or equal to the general dimension. This local dimension defines the number of the corresponding Lyapunov exponents. Given with a sequence of matrices T sub I, we use QR matrix decomposition to find orthogonal matrices Q sub I and upper triangle matrices R sub I, where corresponding diagonal elements of matrix R sub I are the eigenvalues, which we expect will grow like the Lyapunov exponents. The concept of Sano and Savadas algorithm is similar to previous ones. Here we actually define some tangent space with radius epsilon, and here we have some shift operator and linear operator A, which corresponding eigenvectors and eigenvalues stretches our space in some direction and by some values. Exactly these eigenvalues, which are averaged later, will define corresponding Lyapunov exponents. Speaking about recurrent analysis, here we have a recurrence plot. A recurrence plot has been introduced to study dynamics and recurrent states of complex systems. The recurrence plot is an array of dots in a n-square matrix, where dot is placed at the position ij whenever x of j is sufficiently close to x of I, and this mathematically can be expressed according to the following formula. The dots within our pair, representing the time evolution of the trajectories, exhibit characteristic large-scale and small-scale patterns. Such patterns, such as vertical, horizontal lines, different diagonal lines which represent deterministic structures, are the base for the recurrence quantification analysis. So, systems possessing deterministic or rule-based dynamics are characterized by diagonal lines, indicating repeating recurrences within a state. For periodic signals, the diagonal lines are long. For chaotic signals, the diagonal lines are short. So here we can see corresponding measure of recurrence quantification analysis, such as the average diagonal line length, which denotes the average time two segments of the trajectory remain close to each other, and maximal line length in the diagonal direction, which is simply the length of the single longest diagonal within the entire recurrence plot. Since diagonal structures show the range in which a segment of the trajectory is rather close to another segment of the trajectory at a different time, these lines give a hint about the divergence of the trajectory segments. The smaller L max, the more divergent are trajectories. Therefore, the measure of divergence, or diff, according to Ekman, can be used to estimate the largest positive Lyapunov exponent. Thus, as we discussed all the important for us methods, let us represent corresponding empirical results. So here you can see the largest Lyapunov exponent from Ekman's algorithm for computing the spectrum of such exponents. First picture is for window of size 500 days, and the second for 1000 days. And results for the second picture can be better at this procedure, as this requires a lot of data, and it works better with such amount of data. So here we can see Rosenstein's algorithm for calculation of only the largest exponent. And as you can see from this slide, this algorithm is much more stable for the length of the corresponding data, because both for 500 days and 1000 days it looks really resistant to noise. Here is presented Sanoan-Savada's algorithm, and it's also sensitive to the amount of the data as Ekman's algorithm. Nevertheless, it notices the main faults in our index, but we need a large window to get better results. And actually, the last measure is the measure of divergence from recurrence quantification analysis, and as you can see, it's represented to be a good indicator. So when it goes to 0, index is presented to be predictable and stable, and during the crisis period it starts to grow, indicating about chaotic phenomena. During our investigation, it was studied that Lyapunov exponents are presented to be powerful indicators of the chaos in financial time series. Looking at the figure on the right side, we can see that Lyapunov exponents give us confidence that definitely DAX index is presented to be chaotic. Definitely, a lot of parameters should be considered for accurate estimations of Lyapunov exponents, such as embedding dimension, time lag, length of our time series, etc. And only because of misleading one of these parameters, the results obviously is presented to be incorrect. And also we can use our indicator for some random periods, and it can be useful to know when to start trading and when to stop. And also we can use Lyapunov exponents for defining the prediction horizon, namely for defining the time period when two trajectories are remained close to each other. In further, it would be interesting to study other measures of chaos for our purposes and different methods from machine and deep learning. So, if you would like to study this topic more deeply, please ask us. Send your email to me or to Vladimir Nikolaevich, and we will try to find for you the corresponding literature or answer your questions. So, thank you for your attention.